Okay, welcome to part 2 of SpaceGass for Dummies. And I thought we'd fire it up and see what we've done earlier. So here we have a typical three-dimensional frame. It's relatively simple. It's a single-story warehouse, which there's a divided wall in between. And this was relatively quick to put up. You'll see we're displaying the grid with the grid numbers. And you can use your mouse button to move around or drag it around. That's your pan. And you can also use your left mouse button to rotate the building as you see fit. And you can use your scrolling mouse to zoom it in. Now, what we're displaying at the moment is the rendered structure with its sizes done. So I've already done the member selection and the member sizes. I've also done the analysis and done some design results. So all of these buttons are live as well. So this is a relatively simple structure. You've got a color coding down here, which you're supposed to interpret as to, well, this greeny looking thing is possibly a UV 530. Unfortunately, many of the colours look the same, so they're not too good at distinguishing between the colours of the various shades of pink. They've got two pinks, two greens, so it's not always obvious what your members are. I'm also displaying the bases here, and they're looking like they're all fixed, but there's something else going on with the fixity of these bases. So at the moment, I'm showing it rendered, so your display mode is select that. You can have an outlined mode, or you can have a wireframe model. Now, sometimes when you're displaying results, it's much easier to see the wireframe model. We're also displaying the nodes, so we can switch that on and switch that off if we want the nodes on and off. If we don't want to show the bases or the restraints, we can switch those on or off. And again, down here, you've got whether you want the grid on or off. Sometimes it's easier to work with it on. This is generating the grid, so I'll cancel that. We've already generated the grid. One of the nice things is to define a grid, and you can draw your structure around it. That's one way of doing it. You can also determine other grids and determine whether you're looking at the Y-X plane or the X-Z plane or the YZ plane, depending on how you want your grid and how you want to store it. Okay, so again, we'll switch that off. This shows the origin. It's good to know where your origin is so you can know where to increase your coordinate values. Unfortunately, it's rather big, so it takes up a lot of room there. This is the three-dimensional coordinate system. You can use this actually to change your view. So you click on the plan, it gives you a plan, but you can also drag the corner around. So if you want the front, click on the front and so on. So again, you can pull it around, play around, flip it upside down, should you wish. Right, so how did we get there? Well, we've defined our structure. You can define it using a wizard, and there's a portal frame builder or a structure wizard. If you click on that, you can go through a number of different types. There are plenty of other videos that SpaceGass have released will take you through that. And similarly with the portal frame builder. So once you've defined your nodes, you can define your nodes simply by dragging and dropping it should you see fit, and then you drag in another one where you like, and you can define a member by connecting the two. And there's another trick that you'll keep defining nodes and members as you go along. You probably didn't really want that, so I'll see if I can undo that. Or you can select it. Select those nodes, hit the delete button, and that says I'm going to delete my nodes. Something to remember, if you delete nodes, it deletes members connected to them. Okay, so that's drawing the structure. And another way of looking at that is there's always this thing here called the data sheets. And so you can click on the button marked nodes and that'll display all the nodes. And if you really want to, you can change the X, Y, and Z coordinates as you see fit directly in here. This is kind of the old-fashioned way of how we used to do finite element analysis, by defining the nodes by a table. Similarly with members, you've got to click on the member button and that reveals the member data sheet, and the members are listed 1, 2, 3, 4 and so on. They have an angle, we mentioned that in part 1, and so if you want to turn it on its side, you can stick in a direction angle, for example, in this case 90. What kind of element is it? So is that normal, is it tension only, compression only, gable, and so on. So there are different types of elements that you can define in SpaceGass. Most of the time you'll be using probably normal members, but some of your bracing elements you may want to define as tension only. They can only take tension. So that will be a typical cable brace or a reed brace, for example. Over here, you've got the fixity at both ends. So you're defining the thing from node A to node B, what kind of sections. So the sections are given numbers, what material, the materials are given numbers, and so on. So let's close that. Now, the restraints you can put in. So by default, you don't have restraints, but you put them in by selecting a node. And you can select the properties for that, node 40. And for node 40, it's got an X, Y, Z shown here, and it's got a restraint. In this case, it's fully fixed. So you've got 6 degrees of freedom, 3 lateral, 3 rotational. And in this case, it's fully fixed. And we have to do the releases in the members. This is where you can define constraints and master and slave nodes, which we'll come on to in another part, probably part 3, when we go into beams and plates. Okay, so that's where you define the restraints. You can also draw them should you see fit on your grid. And you can do them at multiple times. So if you select multiple nodes, it doesn't know what the coordinates are necessarily. In this case, they've all got the same X and Y, but varying Zs. This is a quick way of changing the alignment of a node, so you see fit, but you can change the restraint on all of them applied globally. Okay, so click escape, and if you press the escape button, it deselects. One of the other annoying things, it doesn't actually apply things unless you press OK. So you can do things like that, and it won't actually apply until you've actually pressed the OK button. Okay, so now you've formed your structure, you've got your nodes, you've got your elements, you've got your restraints, and your members defined. So for each of your members, you need to define what the material is. If you select one, you'll get a hover over it. And this tells you, if you've got very good eyesight, that this is member 107, it's section 11, which happens to be 150 by 9 SHS. The material is 1, which is also known as steel. It's got a length of 9 meters. And it's going from node A to node B, which is node 75 and 74, and its fixity is also shown in that. It gives you some other section properties in there. But another way of seeing that is to reveal the properties, and that shows you down in here. So I've got member 107, here's my fixity, starts and ends. And so if you want to display those, click on the show member fixities. So that shows you've got something defined. Now, again, in common with many finite element packages for structural engineering, it defaults to everything is fixed. And in the real world, that never happens. So you need to go through and release the element ends or the member ends, so you have a more realistic model in there. So again, your default restraint, when you put it in, it defaults to being fully fixed, whereas you need to go through and define the actual fixity of your bases, and that could be pinned or fixed or somewhere in between. Don't forget, you've got 6 degrees of freedom to consider. Now, one of the things I find more useful is define the fixity at the member end rather than in the base. There are reasons for that you'll find out when you start analysing these structures. So member 107, it's section 11. So section 11 is here, and it displays it as a 150 by 9 SHS. How do we get through to there? Well, you've got this database in here. If you click on that, it's picked from a library. So you can decide which library you're using. In this case, we're using the Australian 300 grade or 350 grade in this case for an SHS. From the pull down menu, we could have picked lots of other section sizes, whether it's universal beams, columns, or even welded beams that you can select. It does warn you when some are not available or they're obsolete, which is kind of a nice touch. And there, so you can close that. By default, you can add one by pressing the click button and then select from which item you want. So there's an alternative view. If you've already defined a section, you can use it again and again, obviously. The material, it offers in a similar way. You can select from, in this case, I've got a list of one material, which is steel. If you had other materials, they'd be listed here, and you can choose from different types of material. This is the material rather than the grade, because the grade is put with the actual member. Similarly, you can add a material and go to the definition, and again you've got the libraries here, so we're going to be using Australian definition. So for example, if you're using an Australian aluminium, you can pick that one there. There should be more aluminiums available for you, but this one only gives that. If you've got an alternative, we're probably a higher Young's modulus, then use that. And again, it's about the basic properties are only defined here rather than the full material properties, because the material properties are actually part of the member. If you want a different steel grade, you just pick it as steel, but change the grade within the definition of the section. Okay, close that. You can also define your own section and your own material separately manually, so we'll cancel that. So we have our nodes, we have our members, we have our end fixities, and if you want to, you can switch on or off whatever you're looking at. Now we want to apply some loads, so you need to define some load cases. Switch that off because it gets a bit annoying. So if you go to your nodes, you'll see I've already defined loads. So this is that load case, in our case 127. That's going to be a combined load case. You can simply define, here is a dead load, for example. We've got the dead load from the roof. Now this was defined as an area load, and this isn't easy because it drives you up the wall as to how to do it. Instead of actually defining load planes, you can define area loads by selecting the members, and as long as they're in the same plane, it will allow you to define an area load based on their tributary width. So to define an area load, select the member, and you can either right mouse click or you can use the wizard. And so one of the ways of doing it is there's your member distributed forces. If you just want to list and put in the distribution forces directly, if you just want to put in the distributed forces, you can put it in directly there. Or you can right mouse click and you get another menu coming up here. Where do we go from there? Well, you pull all the way down into loads, and then you've got generate area loads. Do you want them one way or two way? In this case, I'll have them one way. And up pops another wizard. And again, you've got to be very careful of how you use this, because you need to know what load case you're dealing with. And you've got, in this case, a whole set of loads you've already determined. The ones marked red are the ones I haven't actually used. So here's a dead load 3. And if I go OK to that, you tell me what the pressure is. All I can say is 2.5 kilonewtons per square meter. Is it actual or is it projected? And this is quite useful when you're using live load projecting on a roof. Which direction? So these are usually the global loads. And you can also tick this button mark here, generate loads normal to the area in general load area direction. This is more important when you're looking at roofs and projecting live loads upon them. Now, what category is it? So you've defined it in this case as a load category 22. So this is an area load, but if you do something else, it will generate a new area load. Now, you're going to be quite careful, because do you merge the load with that? Do you replace the existing distributed forces? So if that is checked by default, you're replacing the load that's already on that beam. But actually, I don't want that. I want to add to the load already on that beam. And so if you click OK, it adds another load, DL3 in this case, as an area load spread upon those two beams, and so forth. Find out where your load case titles are hidden. Click on the data sheet, and down here you've got a whole column dedicated to loads. So in my case, I don't have any node loads, but I do have some member concentrated loads and member distributed forces. I've got the self load, I've got combination load cases, I've also got load case titles. That's where they are. Click on that. And this is a set I prepared earlier, and you can set up templates in SpaceGass so you can use the same stuff over and over again. And so we're starting with case 1 is self weights. We've got a couple of dead load cases, a whole series of live load cases, and then wind in various directions. And then we've got earthquake, and we've got some basic snow loads. Then you can start with combined load cases. We've started the numbering at 100 and so on. So here are our combined load cases. Where do we combine our load cases? Combination load cases. So we've defined load case 100 as 1.35 G. So here are all the basic load cases, and here are all the factors you're putting in. So similarly, load case 110 is 1.2 G plus 1.5 live distributed. And so you're just picking on the distributed loads and applying a 1.5 factor to that, and so on through the list. Okay, nice and simple. So now we want to analyze. So we've got our structure, we've got our nodes, we've got our members, we've got them connected, we've got them restrained. Now we want to analyze it. So the first stage is click on the linear static analysis. If you leave the load case blank, it will analyze all the loads, or you can choose certain loads. Let's just say if I pick DL3, click OK. So that's just the dead load. So by default, you're picking a linear static analysis. So just click on OK. It runs through analysis in no order of time at all. And then it gives you your equilibrium imbalance, which is a tiny, tiny number. So that's good. Your highest residual forces, again, a tiny number because it's 10 to the minus 12. Similarly with your moment, it's 10 to the minus 12. So these are tiny residuals, which means you've established static equilibrium in your model. Okay, so you could potentially go straight to looking at the analysis results by clicking one of these buttons. So if I click on that, I get the bending moment diagram. But notice I've still got the loads on there, so let's switch the loads off. And so I've got my bending moment diagram just for those particular frames because that's the only load case I'm looking at. Notice I don't have the other load cases because I've only done the analysis on one particular load case. So let's go back to the DL3. Okay. So this is displaying the bending moment diagram. If you want to make it bigger, press M and your scroll button will make your diagram bigger. If you want the numbers to show, click on display. Now that shows everything by default. So if you click the arrow key, I don't want the section names, I just want the annotation. So you can have max or min or both. And do I want to show the units? Yes. How many decimal places? Well, we've got 0 decimal places. It will show the raw numbers. So if I click on OK, it's only showing me the numbers. If I just want to isolate those two rafters, one easy way of doing it is create a filter. So click on the filter button. And so I want another filter and I want to select nodes and select them. So I want, which ones do I want? I want that, 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 and that. And if I hit return, I've now got that as my filter. And it's got those two rafters and just those two rafters. Everything else is grayed out. If we zoom in again, we can see that the maximum moment is 336 kilonewton meters, so slightly higher than the center bending moment. Okay, so that's your bending. Again, you want the shear. Gosh, we've got both. So press the and hold down the S button and you can get a more sensible size for your shear forces diagram. Similarly with axial load, I've got axial load in this due to this loading because I've got an incline in there. The other one people forget is torsion. So arising from this, I've got pretty much no torsion at all. If I make it bigger, I'll tell you that my torsion is tiny, 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 about 0.06 kilonewton meters, so hardly any torsion at all, even though you can make the diagram bigger to pretend. So ideally, you don't really want to be designing your ordinary beams, particularly the simply supported, for torsion. Okay. Don't really need stresses here because it doesn't actually mean anything, because you need, first of all, a render. Scroll up. Let's have a rendered mode. And will the stress actually mean anything? Yes. So if you want to see the stresses within the beam, here we have, you click on the stress diagram and we've got, in this case, a combination of axial and bending stress. You can select which stresses you want to show, which analysis results you want to show. So if you just want the Y bending stress, that's hardly anything because that's your minor axis bending. If you want your major axis bending, you want the Z bending moment. So we're moving from 649 kilonewton meters through to 356 kilonewton meters. And that's the bending moment. Let's see if the bending stress. We see here we're going from plus or minus 197 megapascals in there under that particular load. So that's loaded, that's analyzed. So we'll get rid of the filter. No filter now. We've got loads. So we've got dead load 2, live load, which are generated as area loads. We've got loading from the wind, which we've put on bit by bit as area loads. And then we've got wind in the other direction, loads due to wind in the other direction. So I've got my loading as generated. One thing that's useful to have are these filters. So I've already defined a set of filters, and I've called them after the things I need. So here is roof rafters, so I can filter just for the roof rafters. I can pick the rear columns or the front columns, roof bracing or the wall bracing, and so on. So all of those members are in that, and that's an easier way to display things, to tidy up what you're looking at. Okay, let's take the filters off. So take the loading off. Now we want to do a full analysis of it. So we'll do analyze, linear static analysis. We'll delete that and get all of the load cases analyzed. We'll do a linear analysis. Click on OK. That runs through it. And we've got tiny deviations there, so we're good. He gives you an analysis summary, then disappears. So it posts an awful lot of information without rendering it in place. We also then need to do a buckling analysis if you want to display buckling modes, and to make sure your loading, to make sure your frame is stable and doesn't buckle. And you'll need that when you're coming to design. So buckling analysis, you do all the load cases, and it runs through several iterations until it comes up with the lowest buckling ratio. So the lowest buckling load factor it's come up with is 6.441. So not too high, but not too low. As long as it's over 1, you should have a relatively stable structure. If it's close to 1, you're quite close to being an unstable structure, and it's likely to buckle before it actually starts yielding, and that's not good. So you can click OK. So you've done your linear static analysis, you can do your linear buckling analysis, and you can display your buckling analysis, should you wish, by what looks like Spider-Man there in the corner, and that tells you your buckling and mode shapes. It doesn't tell you a great deal, it just shows load factor 14.1. For that particular load case, if you do a different load case, you get a different buckling factor. So for load case 10, you get a buckling factor of 30. If you do all combined load cases, it tells you individually. So that's the buckling analysis. And again, switch that off, and we can show here's our bending moment diagrams for all of the different load combinations. Let's pick a simpler one. So that's the bending moment diagrams for your combined gravity loading. And switch that off. Assembly with shears, axial forces, and also deflections, and it reads out for each of them. Obviously these deflections are for the ultimate limit state. You need to do serviceability limit state for more accurate deflections. Okay, so you've modeled it, you've analyzed it, you've got your results. If you want, you can just put that as an output, and you can do text reports and click as many reports as you like. What it generates is buckets and bucket loads of pages of analysis results. I'd much rather have the envelope results. So I click on the envelope, and then when you do the output and the text report and use load case titles combined, so on, you can list all those, and you can do the output based upon your member forces, and it should do it just for the envelope. If you click on next, and which filters do you want? Do you want it for the whole, or do you just want it for the roof rafters, for example? Which section properties you can pick down, which load cases you want. So let's have the distributed roof load under gravity. If I click OK, it gives me a report, which you can actually export as a CSV or an Excel file, or you can print it as a PDF. So you'll find these are quite long. I've limited it to a simple set of elements and one load case, and even that you've got quite a long report. The alternative you can do it as a graphic. So what you're putting out is basically what you're seeing on the screen. So if you click OK, you can then view your model. So it often chops things off, and then click on your PDF and it generates your PDF. And off you go. So that's graphical output. So part 3, once we've got our frame analyzed, we might want to design it or check the members if you've already selected the sizes. So we're coming down to here on the left-hand side into the design buttons, and here we have show the design elements. At the moment, these are all my design elements, and you can select them all. You can drag and select steel members. I've basically made every steel member and a design element, and we can then go to design. Obviously, you have to put a fair amount of input to get to this. So design check steel members. I'm going to use NZS 3404. It'll run through as many as you like. You can apply your filters, you can group your section properties, but let's be lazy and just do the whole thing. We're only checking, we're not forcing it to design it. So once you do that, it will run through the design process or the design check. All of the members pass the code check, and that's because I've checked it before. Usually it will fail at some point. To show your analysis results, click on the button down the bottom left, and that's your results. And this gives a very simple output in terms of utilization ratios. So the green, your utilization is basically halved. So basically your load factors. Load factors are the inverse of utilization ratios. So basically, if you've got a utilization ratio of 0.5 or 50%, your load factor is over 2. And your ones that are closer to failing are marked in blue. And then if they're red, it's failed. It'll sometimes come up with a design error. It may be you haven't restrained it properly, or you haven't quite defined all the attributes. So let's go back, and what did we do with that and switch that off? If we pick a design element, for example, you need to input or edit the steel member. That brings up this data sheet, basically. So this is steel member 35. I've given it a name of Eve's beam, and it's taken from a member list of these 4 members. I've got my strength as normal. I could change that if I want. But let's pull forward the design parameters we had in the analysis. The effective length. Now you can actually get it to take your effective length from your buckling analysis as long as you put your restraints in the right place. This is one of the things you need to check. Is it braced in position at both ends? This will often come up with a design error if you don't. Otherwise, even if you've got a member there, it will assume it's not actually bracing it. You can put in your restraints. In this case, our restraint is just at the end. If you want to generate flange restraints in between times, you can click on the flange restraints and apply a number of different flange restraints as well. So we'll cancel that. You can tell it it's eccentric, whether it's connected at the flange or the web, or concentric, and whether your design criteria. So if you're going to design it, are you designing it for weight or for depth, minimum depth or minimum weight, and so on. And it assumes certain things. So you assume, not unreasonably, that your bolted connections are using 20mm bolts. So that allows you to do all sorts of things there. So you've got to be careful that the buckling parameters you're putting in are realistic. So if you're saying it's restrained by purlins, are the purlins adequately connected to the rafters, for example, which actually apply your lateral restraint to the flange that counts. So don't forget, in a portal frame, you've got load reversal and your bottom flange could actually be in compression. Okay, so that was the member design, and you can again output that in your text report by selecting, let's take all off, but let's just have the member design summary. So if I click on next, which I just want the rafters, and for all of the load cases, off you go, and you get this steel member design report. And again, it's many, many pages long. Takes you a long time to get your head around what all of these things mean, but the load factor is basically the design summary. Usually if your load factor is above 1, you're quite happy. These are quite close to 1, but they're still good, and you can work your way through it. If you've asked for the full calculations, it gives you all the description, the section properties, and so on, and then we'll go through each of the design checks. So it might want you to check, and it gives you a warning, have you checked a nonlinear analysis for P delta, for example. So it throws up warnings to remind you to check certain things. So that was steel member design. This thing can also do steel connection design. Steel connection design are down here. So if I escape from that, show me the steel connections. Oh, I haven't got any. So let's define a steel connection. So if I select 2 members, then I can right mouse click, input, edit steel connection. So it's going to be a portal frame joint. Do I want it bolted or welded? Decisions. It's probably going to be, a moment. So you're going to want something that can take a moment. Chances are that's probably going to be welded rather than a bolted end plate, but we'll try a bolted end plate, see if that works. So once you've selected it, another sheet comes up, and it draws you a diagram of that section, and it's saying MCT is less than 1.1. So a critical utilization ratio is 0.97, so that's quite close to the limit there, but generally it's good to go. You might want to check a few things about that. You can use this to generate your drawings. You can export from here DXF and DWG drawings. So you can save it as DXF or DWG and then import it into your CAD file. What if we made it a weld? Does that help? Now, utilization is 0.99. But it's also giving you a warning that your stiffener is not satisfied, your tension stiffener. Unfortunately, you can't do a family of connections, which I'd really like to do, and it doesn't let you do it. So if you go input edit steel connections, you can't make that connection. That to me is a bit of a downer. You just got to pick the worst case and pick that to design. Okay. Let's pause there for today. We'll come back with other beams and designs and maybe go on to plates.